Hello and welcome to another session of our Assumptions of Physics reading group. Today we are going to look at discrete and continuous quantities. So we saw last time what were necessary and sufficient conditions for essentially finding ordering through experiments. So the idea is that you're trying to set up a scale for some quantity, for example, position or time or whatever other quantity, and you have some references that tells you the value is below this reference or above this reference. So that could be ticks of clocks, notches of a ruler, or voltage levels for an AC/DC converter, and for a digitizer, not an AC/DC converter. And then you're basically asking what are the properties that all these references must have such that I can say that what I'm actually trying to measure, trying to identify is a sort of a linear sequence of values such that then if I know that it's before this reference and after this reference and so on, you can assign a number, a numeric quantity for that value. So basically we're trying to understand how from metrological considerations one can get the mathematical structure that one has with order topology. Essentially, that's what it boils down to. So we figured out the hard part last time, which was the necessary sufficient conditions to have this ordering, and now that we have this ordering, we want to understand what are the extra conditions that make this order discrete so that it gives us integer values, and what are the conditions that makes it a continuous real valued quantity. So it's gonna be just me and Tobias for now, so we'll start and hopefully other people will join. So as usual, I need to share the, where is it? Share the text and share the link on the chat if people want to look at independently. There you go. Let's see if the sharing is working.
I can see the screen.
Very good. I can make it a little bit bigger. There we go. You can start.
Okay. Now that we have seen the general conditions to have a naturally ordered experimental domain, we study common types of quantities and under what conditions they arise. We start with discrete ones. The number of chromosomes for a species, the number of inhabitants of a country, or the atomic number for an element are all discrete quantities. These are quantities that are fully characterized by integers, positive or negative. We will see that discrete quantities have a simple characterization. Between two references, there can only be a finite number of other references. The first thing we want to do is characterize the ordering of the integers. That is, we want to find necessary and sufficient conditions for an ordered set of elements to be isomorphic to a subset of integers. First, we note that between any two integers, there are always finitely many elements. Let's call sparse an ordered set that has that property, that between two elements, there are only finitely many. This is enough to say that the order is isomorphic to the integers. In fact, if an ordered set is sparse, we can always go from any element to another in finitely many steps. Therefore, we can pick one element, call it 0, go forward one element at a time, and assign a positive integer to all the following elements, or go backward one element at a time and assign a negative integer to all the preceding elements.
Yeah, maybe I can go through the definition, so it's not always you talking. So basically now this is a little bit of order theory that allows us to set up some of these concepts. So a chain is a linearly ordered subset of an ordered set. A chain between two elements is a chain where the two elements are the greatest and the smallest element. So you have, in general, a partially ordered set. You identify two elements, and then you say, I go from one to the other. There is a sort of a linear order that one is always greater than the other that connects the two. So this is a standard concept. This definition is instead ours. An ordered set is sparse if every chain between any two elements is finite. Basically, at some point you have immediate predecessors or any immediate successors. You can't always put in something in between. And then the
Just one
corollary.
question. So
Go ahead.
the chain can be infinitely long, though. Like it doesn't need to be a chain between two elements. Is that right? Or do we always
Yes, the
calculate?
chain itself, yes. If the chain has two elements, is a chain between two elements, then you have a greatest and smallest. So the real numbers are a chain.
Okay, okay.
Yeah, so a chain is basically just something that has a linear order, meaning that any two elements, either the first is before the other or the other is before the first.
Okay.
Yeah. And so sparse basically means that at some point the elements in between stop.
Mm-hmm.
Every element in a sparse linearly ordered set that has a predecessor has an immediate predecessor. So if in a sparse linearly ordered set there is something afterwards, then there is something immediately afterwards. And of course, if there is something before, there is something immediately before.
Mm-hmm.
And again, this is one of the things that are obvious, but you have to prove it and so on. And then the converse of the corollary, that a linear ordered set in which every element has a predecessor or successor, has an immediate predecessor or a successor, is sparse, is not true. So for example, you consider the integers with the following order. You first put all the non-negative one, and then you put all the negative ones. And so you put the infinity in the middle.
Mm-hmm.
Right? So every positive is always before of every negative, and every negative is always after every positive. So all elements have an immediate predecessor and successor, or no predecessor or successor, like the 0 and the -1, yet 3 and -3 have infinitely many elements in between.
Mm-hmm.
So these are always the fun things with infinity that you can find an interesting counterexample. So if we have a sparsely ordered, we have immediate predecessor and immediate successor, but it's the converse is not true. A linear order is sparse if and only if it is isomorphic to a contiguous subset of the integer. So if you have something where you have a linear order, and at some point the elements in between, you can only have finitely many elements in between, then this ordering is a subset of the integers. And this is exactly what we said in the first explanation. You take the one element as 0, and then you go afterwards and you go before, and at some point you can reach any elements, because every element is a distance finitely many elements from another, and so you're going to be able to assign an integer, and that's it. So what I'm basically doing here, it's something similar to what we're going to see later. That is what Cantor did for the reals. He characterized the reals as a particular type of ordering, and so here I am characterizing the integers as a particular type of ordering, such that now we can say, okay, this order is characterized by having a relationship between the references.
Mm-hmm.
There we go. And if you guys have questions from the chat, I'll keep an eye, but let's continue.
Okay. We can now define a discrete quantity as one for which the ordering is sparse. While this may typically correspond to a set of contiguous integers, it is not necessary. For example, the set of names ordered alphabetically, the set of orbitals for a hydrogen atom, the possible energies for a quantum harmonic oscillator. These are all discrete quantities, even if the label we use is not an integer. The natural question now is, under what conditions are the probabilities of a domain ordered like integers? The answer is straightforward. When the references within the domain have a sparse order. That is, between two references, we can only put finitely many ordered references.
Right. I'll go.
We just convert like the abstract order thing. We just talked about numbers now, and now we just translate it into experimental domains.
Yeah.
Okay.
Yeah, and the ordering, for the other type of quantities is whatever order that you had decided. A lot of the time you actually have an order anyway. So now we have that a discrete quantity for an experimental domain is a quantity for which the ordering is sparse, so that we don't have to say that these are the integer. We just say that the ordering is sparse, which is isomorphic to the integer, so that's fine. And then we have, and now there is the theorem here. Now we have an experimental domain, and then we want to have this equivalence. The domain has a natural sparse order. The domain is fully characterized by a discrete quantity, and the domain is generated by a set of refinable strict references with a sparse order. Right? So the idea then is that we can, so we saw before that if we have, if the domain is generated by a set of refinable strict references, we get an order. And now we basically impose the order on the references themselves. So we can say, I have two references, one comes before the other, and they're linearly ordered, and I can't put something in between. Then you can get, you're gonna get the discrete quantities. So as we said last time, we're not going to go through the proof. I don't remember exactly what. I haven't looked at this proof for a long time, so I don't know if there is something interesting. This proof is quite short. This is the type of thing of you prove 1 to 2, 2 to 3, and 3 to 1. And so the part that would be probably interesting would be this part, but I don't recall whether there was actually interesting. So here we're basically using the ordering on the references themselves, because we defined when a reference is before another. And so if you assign that, you basically have these references that are going to be, one after the other. And the point is that when you have an immediate successor of a reference, if you remember, then there is no gap in between. So essentially the on conditions are one right after the other, and so the on conditions of these references essentially are enough to cover the whole space. That's essentially what I remember happening. Yeah.
Okay. Now,
Alina,
sorry?
No, I'm saying if Alina wants to read, or we just have to be a three.
Yeah, I can read.
Please. I mean, I don't mind the order. We are now 2. Right.
So now consider the examples above of discrete quantities. In each case, we can experimentally test whether we have a particular value or not. For example, we are always able to tell whether there are exactly 3 apples on a table or not. This is not a coincidence. There is a direct link between the ability to have consecutive references and decidability. So should I read the footnote, perhaps?
Oh, yes, forgot.
Footnote 5, recall that this is not the case with continuous quantities. Does it say quantities? I think that's a typo. No, it's correct. Sorry,
okay.
I mean, yeah. Sorry.
Too many TIs. There's a double TI that they have.
Recall this is the case for continuous quantities, and we're talking about being able to tell whether there is a particular number of things or not. Because of finite precision, we're able to exclude that a given particle has exactly 0 mass, but it is not possible to conclusively show that it has 0 mass.
Yeah.
Okay. As we saw before in 3.31, two consecutive references are such that the before statement of one is equal to the negation of the after statement of the other. But since before and after statements are both verifiable, it means their negation is also verifiable. That is, they are decidable. And since before and after statements generate the domain, all statements in the domain are decidable. It turns out that this will work in reverse as well. Whenever we have a domain consisting of only decidable statements, we can always create a discrete quantity that fully characterizes the experimental domain.
So this is something that it's kind of important. So the order topology of the integer is discrete because each singleton, like if you take a value z, then you can say the element is less than z plus plus, the z plus 1, and the element is greater than z minus 1. And that's exactly that element. And since the before and after are open sets, like they're verifiable statements, then the singleton itself is the intersection of two open sets. It's an open set. It's the end of two verifiable statements is a verifiable statement. So every possibility is verifiable. Every singleton is an open set, and then you have the discrete topology. And therefore, an experimental domain is decidable if and only if it is fully characterized by a discrete quantity. So if you have an experimental domain that is decidable, you have a discrete topology, and then you can basically define an arbitrary ordering, and the topology is going to be the topology of that ordering. So it's like what you do in databases where you have a bunch of words and then you assign numbers to each word and then you basically store numbers that actually mean words, even though there might be no intrinsic ordering in what is it that you're trying to describe.
Okay. Note that since any discrete order leads to a decidable domain and a discrete topology, any reordering of the possibilities will give the same exact domain. This means that while we can always assign a natural order, the order itself may not necessarily be meaningful. For example, we can always take a finite group of objects and arbitrarily assign each a unique integer to identify it. In the discrete case, that's where was I? Sorry. In the discrete case, the domain itself is not enough to pick a unique order, though the set of aligned references that are used to generate the domain is. Wait. In the discrete case, the domain itself is not enough to pick a unique order. Yeah, we've seen there are many, though the set of aligned references that are used to generate it, the domain is. Okay, that makes sense. Also note that for the link between decidability and discrete quantities to apply, it is crucial the quantity is measurable, that we can actually experimentally ascertain its values. Consider the domain with the possibilities. There is no extraterrestrial life, and there is extraterrestrial life. We can arbitrarily label 0 the former and 1 the latter. But since we cannot verify the first statement, we cannot really measure 0. In that case, the domain is fully identified by the discrete quantity, but not fully characterized.
Okay, so this is what we talked about a few weeks ago, that you might be able to get the points, but you don't have the right topology because those points are identified by a different set of verifiable statements. The thing that I want to make clear is that sometimes people erroneously think that topology is about ordering, and there are some philosophers that go around saying that, and that's not true, and or that it's about distance. It's only about a distance where when you do not have essentially a discrete domain. If you have a discrete domain and you have a distance, that distance function generates the topology, but any rearrangement will also generate the same topology. This is kind of the same in even on the continuum. The fact that you have a distance function that generates the topology, it doesn't mean that you can recover the distance function from the topology. In fact, on the reals, any distance will generate the same topology, and so you can change your distance and you still have the same topology. So it's not true that the topology only capture experimental verifiability, and that's it. And so again, what is important here is this idea that it's the quantity that is telling you what the ordering is, or there is an order put on the domain. But you have to know what the order is. It's not something that you can recover from the topology.
Arbitrary precision and continuous quantities. Second type of quantities we want to consider are continuous ones. The average wingspan for a species, population density of a country, or the mass of a proton are all continuous quantities. These are quantities that are fully characterized by real numbers. We will see that also continuous quantities have a simple characterization. Between two references, there can always be an infinite number of other references. Similar to what we did for the integers, we want to characterize the ordering of the real numbers. This will be a little bit more involved, as we will need a few more requirements. First of all, we know that between two real numbers, there are always infinitely many real numbers. It's called dense, an ordered set that has that property. This is not enough to identify the real numbers, though. The rational numbers are also dense. Should we go for a bit longer, or
I think I can take over. One reason real numbers are used over the rationals is that they contain all the limits. This property can be restated in terms of ordering in the following way. Suppose Q is a linearly ordered set. Take a set A, which is a subset of Q, that is bounded. That is the set B of all Q's in Q that are bigger or equal than all A's in A. Yeah, of elements that are greater than all the elements of A is not empty. So, okay, that means we have a bounded set.
Yeah.
Then we say that Q is complete if B has a smallest element. One can show that the rationals are not complete. Say A contains all rationals less than pi. Then there is no smallest rational value that is greater than all elements of A. So this is basically, there's always a supremum, but it's we have the limits if the supremum is a maximum. Is that the same?
Yeah, you don't have a supremum. You have upper bounds, but you do not have a supremum. The supremum is the lowest upper bound.
So we don't even have the supremum.
Yeah, you do not have the supremum.
Okay. Okay.
Because the supremum would be the real number pi, which is not there in
I see.
in the rational.
Okay. Okay, dense and complete linear orders exclude both the integers and the rationals, but they don't pick out only the reals. To do that, we take advantage of two results of order theory. The first is that all dense, countable, ordered sets are isomorphic to the rational numbers. Dense, countable, ordered sets. Okay. The second is that from any linear order one can construct its completion, i.e., you add all the missing limits, which is unique up to an order isomorphism. So suppose that Q has a countable subset that is dense in Q. That is, for every two distinct elements, Q1, Q2 in that subset, where Q1 is less than Q2, we can find an element Q such that it fits in the middle. If Q is dense, Q will also be something
Dense, yeah.
dense, and therefore will be order isomorphic to the rationals since it's countable. Okay, if Q is complete, then it will be the completion of its dense set Q, and therefore it will be order isomorphic to the reals.
That's basically Cantor's characterization of the real numbers. So the real numbers contain a countable dense subset, which is the rationals, and they are the completion of the rational. And since the completion is unique, and since every countable dense order is isomorphic to the rationals, then you always get the reals as a completion. So that's basically the idea. We can go through the definition. An order is said to be dense if between any two elements there exists an infinite chain. So now, before we had always finite chain between every two, when we said there was sparse, now we always have an infinite chain. An order set is dense if and only if between two elements we can always find another one. It's easier to see it also like that. And a subset of a linear order set is dense in Q if when we take two elements in the whole ordering, you can always find something in the subset that fits in the middle. So again, there are different notions of dense. Dense was, an order is dense if between any two elements of the order you can find another element of the order. This is a subset is dense in another order, in the overall ordered, if you can put an element of the subset in between every two elements of the order. And then a linear order is complete if every non-empty bounded subset has a supremum. So given an A, you take all the elements that are greater of all elements of A, those are the upper bounds, and then you say that element is not that set is not empty and has a smallest element. And then this is the essentially Cantor's theorem. A linearly ordered set is dense, complete, and has a countable dense subset if and only if it is ordered isomorphic to a continuous subset of the reals. And proving this is much bigger, and so we just take this as a result from order theory. Okay.
Okay. We can now define a continuous quantity as one for which the values are a contiguous subset of the real numbers. While in principle we could define it on a generic set that is order isomorphic to the real numbers, we do not have any other example of such a set. The natural question now is, under what conditions are the possibilities of a domain ordered like the real numbers? The answer is straightforward. When the references within the domain have dense order, that is, between two references, we can put infinitely many ordered references. Intuitively, between two marks of a ruler, we can keep putting finer and finer marks. Note that the dense order on the references is enough to get a dense complete order on the possibilities that has a countable dense subset. The completion comes without extra conditions because experimental domains are closed under countable disjunctions. New references, in fact, can be constructed as limits of others, and since they will be just other references, they will have the same properties. The countable dense subset simply corresponds to the countable basis of the domain.
Okay, so this is something that it's sort of nice, is that we're going to have a characterization essentially exactly like before. As we said before, if you just have a dense subset, sort of a dense ordering, you could get the rationals. And so you need something to rule out the rationals and actually get the reals. And the thing that is nice, it's exactly the closure of the topology under countable union that works, that does that work for us for free. We don't have to put any condition. And somebody wants to go and look at more detail, of course there is the whole proof, but that's basically the gist. And the fact that we have a countable dense subset in the ordering comes because we have the countable basis. So we're going to have a countable basis. We're going to basically be able to make references with the countable basis. And then what's going to happen is that you can create this set of references that are that have a denser ordering and that are countable and they're dense in the linear order of the whole domain, and therefore you recover and you say, these are the reals. So the definitions are: a continuous quantities for an experimental domain is again a quantity u less than q, where u is a continuous subset of the real numbers, and we use contiguous just to make things easier. Of course, one in principle can then join different subsets and make something more complicated. We just don't call that a continuous quantities. It's going to be some other more complicated things, but in principle you can have it. And so now we have, as before, dx is an experimental domain, then the domain has a natural dense complete order that has a countable dense subset. The domain is fully characterized by a continuous quantity, and the domain is generated by a set of refinable aligned strict references. This gives us the order, and then you say that have a dense order. So now the references themselves have a dense order, which means if I have a reference, for this tick of the clock and this tick of the clock, I can always put a clock in the middle of the two, and then in the middle of those two, and then middle of those two, and I can always put ticks inside. Right? So that's basically the requirement, which again makes sense from a sort of that's what we assume in practice. We can always refine and make our experiment better and better precise. And so, as I said, I skipped the proof, but the main point that I said were there. It's what really allows us to get the completion is the topology.
Okay. Another way to think about the verifiable statements of a domain characterized by a continuous quantity is in terms of finite but arbitrarily small precision. That is, when we measure a continuous quantity, we can verify statements of the form the value is 1 plus minus 0.5. The verifiable statement is in terms of a range, and the extremes are rational numbers. It is instructive to know then that the topology for the real numbers can be generated by those types of statements. In terms of references, this means that all our verifiable statements could be expressed as verifying that the value is between two references from a countable set of possible references. This again maps well to what one can and does do in scientific practice. Mathematically, we call the standard topology on the real numbers the one generated by the open intervals between rational numbers. And we can show that this is exactly the order topology. Moreover, every verifiable set is the disjoint union of open intervals.
So these are standard results from topology. We call standard topology on the reals, the one generated by the collection of sets that are open intervals between rational numbers. And then you can show that this is exactly the order topology. Or you can define the standard topology of the real as the order topology and then find that that it's the one generated by open intervals. You can do it whatever you want. It's the same thing. And then another standard characterization is that every open set in the topology is the union of countably many open intervals. And this is because if it's the one generated by open intervals, if you are making the union of two open intervals, well, the intersection of two open intervals, it's either an open interval or it's nothing. So the intersection of the intervals don't give you anything else. And then if you take two open intervals and you do the union, either you have another open intervals because there was an overlap, or it's the disjoint union of open intervals. And so when you put these together, you are going to just have the disjunction of open intervals. So that's what open sets for on the reals are.
In the previous section, we saw how the ability to have consecutive references is linked to decidability. In the case of continuous quantities, the inability to have consecutive references means we cannot have decidable before or after statements. Otherwise, we could use them to create consecutive references. So while for the integer quantities, references have immediate successors and predecessors and all statements are decidable, for a continuous quantity, references do not have immediate successors and predecessors, and the statements are only verifiable. We stress here that it is the immediate successor of the references that matter, not the immediate successor of possibilities or values. Take the rationals, for example. As values, they do not have immediate successors of predecessors. Their order is dense. But we can construct a reference with the rational quantity is more than pi. This is a statement, right?
Yeah.
The rational quantity is more than pi as an after statement, and a reference that has the rational quantity is less than pi as a before statement. Since pi is not a rational number, there are no values in between. The two references are consecutive. This could never happen with the reals because all limit values are possible values. So while the rationals do not admit consecutive values, it's only the reals that never admit consecutive references. Yeah, interesting distinction there. Yeah.
Footnote?
Oh yeah, footnote 6. Mathematically, this construction corresponds to the Cauchy limits of the Dedekind cuts one uses to construct the reals. The idea is that experimental domains already have them built into their structure in a way that corresponds better to physical concepts.
Yeah, so that's essentially what I was saying before, right? So if you take the rationals, you can construct these two statements, and therefore you're able to construct references that don't have anything in between. And therefore, you can't say that the references, the order that you put on the references is dense, because you have something, you have two things that you can't put anything in between. So if you want to be able to always put something in between, then you really have the reals and not the rational. And so now we have a slightly different characterization. A naturally ordered experimental set dx is characterized by a continuous quantity if and only if none of the verifiable statements are decidable except for the certainty and the impossibility. So it's like you can see that they are diametrically the opposite of the discrete quantities. Discrete quantities, you have a discrete domain, so every set topologically is Klopen, and every assertion that is verifiable is also falsifiable. Here, the reals, the ordering of the reals, the continuous ordering, is exactly the opposite. Every verifiable statement is not falsifiable, except the certainty and impossibility. So this is why these two orderings are sort of the one that are mostly prevalent. You're making exactly the opposite assumption. And yeah, so there is a little bit of proof, but I mean that's the gist is what we said before.
Okay, the integers and the reals then are the only two possible orders defined experimentally that are, in a sense, regular. That is, the order relationships look the same no matter where you are in the order. You have an immediate successor or not, regardless of what reference you have. You can only put finitely many references or not between any two references. For any other ordering, instead, some references will have an immediate successor and some won't. In this sense, integers and reals are very special, and that is why they are fundamental in physics.
When
Okay.
ordering breaks down, oh, sorry.
No, nothing. I was just pausing to see if there were any questions, but we can continue. Yeah, go ahead.
Okay. When ordering breaks down, as we have identified the necessary and sufficient conditions to define an order from experimental verification, we can reflect on whether these are achievable in practice or they are idealizations. We need to be able to create references that are strict, before, on, and after mutually exclusive, aligned. References can be fully before or after each other, and refinable. Overlapping references can be divided into finer sequential ones. Are these always reasonable expectations? In the case of discrete quantities, they indubitably are. The domain is decidable, so the possibilities themselves are verifiable statements. We can actually confirm that there are 3 dogs in the table. Therefore, it is clear this can be and is achieved. In the case of continuous quantities, instead, things are a lot more problematic. In some cases, you start with what you think is a continuous quantity, then you realize that it was a discrete one. For example, an amount of water seems continuous, but if you keep refining your references, you see that it consists of discrete molecules. That is, you can't really go on refining references indefinitely. That's not the only way the continuous order can break down.
Suppose you want to refine the marks on a ruler over and over, getting more and more precise position measurements. You start with 1 millimeter thick lines, you reduce them to 0.1 millimeter, and make more of them, and so on. At some point, you'll reach single molecules or single atoms, but those have spatial extension as well. We can reach fundamental particles, but those too have an extent, i.e. their wave functions can overlap. We can imagine using more wave-like features, but the spatial resolution will be linked to higher and higher energies through higher wave numbers. So it is not clear if we continue having ever finer references. On a similar note, if a reference is in the end realized through a set of particles, it stands to reason that if we reduce the number of particles, the references will become finer. If single particles are the finest reference, we don't have that many choices. But how are we going to be able to tell our references apart since, for example, all electrons are indistinguishable from each other? How can we place them ever increasingly close to each other so that they don't scatter or switch place? Yeah.
Moreover, it is not clear how our references can be strict. That is, that the object we measure is always either before, on, or after the reference. If the object we are measuring is of smaller extent than our references, then we can reasonably pretend they are strict. But if both the references and what we are measuring are single particles, it will seem that we have a problem. It would appear then that the conditions for a continuous quantity can never really be ultimately met. And if those conditions can be met, it's not that we don't have the real numbers, we don't have ordering at all. Strictness, alignment, and refinability are requirements for order in general. And if space and time can be truly given an ordering, other derived quantities like velocity, acceleration, mass, energy, and so on will inherit the problems. Okay.
In both cases, the real numbers are just an approximation we can make by pretending we can get finer and finer strict and aligned references. This may be contrary to the way many people see the relationship between mathematical and physical objects. Some may feel that geometric description, with its infinite precision, is the perfect one, while the physical one, with the inherent measurement bounds, is the less precise one. Actually, it is quite the opposite. The bounds of a measurement better qualify our description and knowledge, while the geometrical description provides a simplified, idealized, and therefore less precise account. In other words, 3.14 plus minus 0.005 is an exact physical description, while pi is the approximation.
We again stress the fact that the approximation can break down in different ways. It may break down because we reach a finest element, or it may break down because we do not have finer, strict, and aligned references anymore, which is what we expect to happen for space and time. We'd have a structure where coarse references at some point are, to a good approximation, refinable, strict, and aligned, and therefore approximately ordered, while the really fine ones are not. Note that a lot of physical ideas and mathematical tools rest on the idea that there is a well-defined ordering. Causality and deterministic motion require that time is linearly ordered. Differentiation and integration also require the reals to be linearly ordered. All these tools, then, need to be fundamentally reshaped. The general theory, then, is telling us that there is a lot of work that needs to be redone if we are to construct a physical theory that works in those regimes.
And I have no idea how to do it. That's another thing. And I'm also realizing that what I haven't written here, and everything that I realized afterwards this was written, is that alignment also has to do with essentially synchronization. So if you imagine that you have two clocks, it's not that you just have the ticks of each clock. You need to be able to always say, oh, the tick of this clock always happen before or on or after the tick of the other clock. You can imagine that you might have jitter on each of the clock. So you might have that in some cases, yes, they're on exactly the same time. In some cases, one is before the other. In some other cases, the other one is, right? So if you can have perfect synchronization, you can have perfect ordering because the ordering relationship between the ticks of different clocks, it's not always the same. Then there is an issue of repeatability in the same way. If the clock has jitter, but it always has jitter in a different way, if you restart the process and try to measure how much time has passed between one thing and the other, you might find that the tick of a clock happened before or after the event that you're looking. And so again, you don't have perfect synchronization between the object that you're measuring and the clock, and therefore the ordering is not going to be perfect, and therefore you can't define a linear order. And so I do not know exactly what the solution of that is, but the problem is the more we want to have a more complete and perfect description of the physical theory, the more the issues of the experimental setup counts, because some things are going to be due to that, and I don't see anybody actually looking at these problems when they're developing theories of quantum gravity or whatnot. how do we measure things is always a thought as an afterthought, like, oh yes, of course there are these quantities and of course we can measure them. And I think that's a fundamental classical way of thinking. It's yes, these quantities are there and exist independently of what we do and their measures set up, and therefore I don't have to bother thinking about that, and I think it's a problem. Okay, we can effectively read the summary and finish.
Great. In this chapter, we have seen how our general mathematical theory of experimental science handles properties and quantities. These are what we typically use in practice to distinguish between the possible cases and are what we measure experimentally. Mathematically, each possibility is mapped to an element of a topological space whose verifiable sets correspond to verifiable statements. This construction maps to what happens in manifolds, where the points of the space are in one-to-one correspondence with the suitable Euclidean space. Our construction is more general and works for non-numeric properties as well. We have seen that quantities are particular types of properties characterized by a linear order. In this case, the topology is the order topology given by the linear order, which represents the ability to experimentally compare two different values and tell which one is greater. The property ordering theorem and the domain ordering theorem give us the necessary and sufficient conditions under which an experimental domain is fully characterized by a quantity.
To construct a system of measurement for a quantity, we said that all we need is to define a set of references, that is, objects that partition the cases into a before and after. In general, though, references can overlap as they will have some physical extent and may not be aligned. The reference ordering theorem tells us that an ordering on the possibilities emerges only if before and not after statements are ordered by. Sorry, I think I skipped a line.
Yeah, although if the references are
Sorry. The reference ordering theorem tells us that an ordering of the possibilities emerges only if the references are refinable. That is, we can always break apart overlapping references. Aligned, the before and not after statements are ordered by narrowness, and strict, the value is always either before, on, or after the reference. We defined discrete quantities as the ones that can be associated with integers, and continuous quantities as the ones that can be associated with real numbers. Physically, the defining characteristic of the first is that between two references, you can only put finitely many references, while the defining characteristic of the second is that between two references, we can put always infinitely many. Mathematically, the ordering in the second case is automatically complete because experimental domains will already contain all the limits in the form of countable disjunctions. This is the end, right? I'll just read the last thing then. It is important to note that the requirements for continuous quantities cannot really be physically realized. Continuous quantities then should really be thought of as an idealization, the limit of an infinite process of subdivision. To go past the idealization, either we lose the idea of having infinitely many references between two, in which case we revert to discrete quantities, or we lose the ordering altogether.
We reached the end of the book that is finished. The next chapter is the ensemble spaces. I don't know if we want to read it. It's still something that I'm sort of working on. In fact, I just integrated something last week. So we'll have to decide what to do and how to continue this. We could transform it into just a more general open session of discussion. I was also, for that it also might be interesting to move it over the weekend, maybe on a Saturday at 11 a.m. so that more people can join, and 11 a.m. should be a better time because it works both for Europe and for the west coast of the United States because let's see, 11 a.m. It's like 8 a.m. So it's a reasonable time. So we could try to do that. I can post around and see if people are interested, if there is some response. Otherwise, if people have ideas, I'm always open.
Yeah, I suppose like.
Go ahead.
So by post around, you mean like proving for interest in different places, trying to get more people? Like you mean trying to get more people?
Yeah.
Yeah, I mean we could give it some time to maybe see if more people join, and then we do another poll to see what time works. I mean, yeah, I do think 11 a.m. should be generally okay. But in just people confirming is also a good idea.
Yeah. I will do that on Discord. I don't know if there are any questions from the chat. There haven't been many viewers from YouTube today, so I don't know if how many people are there and actually watching. And so I'll wait the usual 30 seconds to see if questions from the chat appears, and otherwise we close. And so we are not planning for now a meeting for next week at the same time. We'll confirm if people are interested. I'll confirm, or if we have something through the posts on YouTube on this channel. Okay, so no questions have appeared. So bye everybody. Thanks for watching, and we'll see each other at some point. Bye.
Bye.